Okay, so I think we should make a start. So we've got some interesting new project proposals for new scanning projects over at CISC. One from Giulia Cabbai, and then the second part of the session is with Jamie Ward. If you can try to keep your mics muted during the talk, there should be time for questions in between each of them. And by all means, write in the chat if you have any comments or questions, and we'll hopefully get to discuss those. So without further ado, over to you, Giulia.
Okay. So, hello everyone, and welcome to my talk. Today I'm going to present you the first fMRI study of my PhD, actually the first ever fMRI study of my life, so I will be really happy to know about your comments, feedback, everything you might want to say. So, as the title suggests, the main topic of this project is mental imagery, a term you're probably familiar with, which is our ability to conjure visual mental representations in the absence of corresponding sensory stimulation. And what in particular I would like to tackle in this project is, and I'm fascinated by, is the great variation in the experience of mental imagery among the general population. It's considered one of the most remarkable individual differences in psychology. So on one side, there are people that report that they say that they're able to imagine an apple as vividly as real life. And on the other side, there are people defined as aphantasics that seem to lack the ability to voluntarily conjure visual images, a term that was coined by Adam Zeman in 2015. On the other hand, I'm also interested in a type of imagery that has been quite neglected in the literature, which is involuntary kinds of imagery as opposed to the classic voluntary visual imagery. By involuntary kind of imagery, I mean imagery that, for example, is intrusive, negatively valenced, and it follows typically a trauma, very common in PTSD, or more synesthetic kind multimodal imagery that is triggered by stimulation in another sensory modality, which will be the one I will focus in this project. So what we know about the neural correlates of imagery, it refers mostly to voluntary imagery. So we know nowadays that imagery involves a large network of areas that span from frontal areas to parietal areas, right back to primary sensory areas. In the case of voluntary visual imagery, occipital areas. However, we don't yet know which area is crucial for its perceptual experience. For example, there's been mixed results regarding the role of V1 in those studies that just look at its increase in bold activity. And however, an increasing amount of study who's adopting a multivariate pattern approach were able to actually decode imagery from early visual areas despite a low bold amplitude response. In contrast, instead, the specific regions that are activated during voluntary imagery remain unclear. However, last year I found this study I was really excited to find out about, a study by veteran colleagues that for me represent a first example of an investigation into the neural correlates of spontaneous forms of imagery. So basically in this study, in the first experiment I'm pointing here, the authors asked participants to line an fMRI scanner and to just listen passively without any task, any other instruction, to a different sequence of natural sounds. I think there were 3 sounds that were presented to them, intervaled with silence. And in a following study, the authors also added a condition in which they cued participants to imagine, to generate auditory imagery of the specific sounds. And what they found in both of these studies, the amazing finding for me is that they were not only able to decode the specific sounds from auditory cortex, but also from early visual cortex, V1, V2, and V3. So the 3 kinds of sounds led to patterns that were specific to scene content in the visual cortices. And also, in these two experiments, the participants had their eyes closed, but in a in a subsequent experiment, the participants had their eyes open, and the decoding accuracy, as you can see in this case, in the early visual areas is slightly lower. So that might also indicate that there is some involvement of eye movements. But in general, what made myself wonder about this study is what is the nature of the representation induced by sound in visual cortex. For me, that was spontaneous imagery, although the authors didn't define it this way. So my idea is to adapt the paradigm from veteran colleagues and basically exploit the evocative power of natural sounds to investigate visual imagery while participants lie in an fMRI scanner. The first addition that I want to make compared to veteran colleague study is to equip my participants with an eye tracking to control for eye movements, and also because it can be an interesting exploratory measure. The second thing I want to do is to add a voluntary visual imagery condition in addition to the spontaneous imagery condition, which is the passive listening condition. So in doing this voluntary visual imagery condition, I want to ask participants to engage in visual imagery while they listen to the sounds. Another important point that I want to add is to take into account the role of individual differences in voluntary visual imagery by considering also potentially extreme groups such as aphantasics and hyperphantasics, those that are able to imagine as vivid as possible. And finally, what I want to consider is also take subjective ratings of vividness on a trial-by-trial basis during the voluntary visual imagery condition. So before going into the specific hypothesis research questions, I want to describe quickly the main task, which will help you to understand better the hypothesis. The idea is that participants will undergo one scanning session lasting around 1 hour, and they will have to perform a task composed of 2 main parts. Part 1 will be about spontaneous imagery. So basically, they're instructed to listen passively to the sounds. What is crucial about this part is that it will always come first, and second, they have to be naive when they come to the scanning session to the fact that their study is about imagery, in order for their imagery to be as spontaneous as possible during this part. So I want also to maintain them engaged by asking them some questions. So asking them to do a task during this part. My idea is to ask them about pleasantness of the sound that they listen to. But yeah, I'm happy to discuss about other options. What I don't want is that in order to answer to the behavioral rating or question, they don't use imagery. They are not forced to use imagery to respond. The second part that will always come afterwards will be about voluntary imagery. So this time they're instructed specifically to engage in visual imagery while listening to the sounds, and they have to rate after each sound the vividness of imagery generated. So coming to the more specific research questions, so I want to tackle my questions from both an univariate and multivariate approach. So first, in my univariate analysis, within participants, I want to contrast activation during voluntary and spontaneous imagery. So I want to test whether there's any difference in activation in my regions of interest, that will be frontal regions and also early visual areas, between the spontaneous and voluntary imagery. Second, I want to test whether subjective imagery vividness, again within participants, will be reflected by a differential activation in early visual areas. And finally, I want to compare my activation in my different groups of participants. So test whether V1, for example, activation will be modulated by individual differences in visual imagery. Regarding the multivariate analysis, the first thing I want to do is somewhat to repeat the same analysis that veteran colleagues did in the experiment, but considering also the voluntary imagery condition. So can we discriminate between specific sounds in early visual areas, for example, within the voluntary and spontaneous imagery rounds? But I don't expect to be able to discriminate between specific sounds in all the participants. What I expect is that I have different results based on the group of participants. Let's consider, for example, there are 2 possible scenarios that I see here, and let's consider decoding accuracy in early visual cortex V1. one possible case is that during both spontaneous imagery and voluntary imagery, people who are better in imagery, such as hyperphantasics, have a decoding accuracy that is above chance, while aphantasics in both the condition score have lower score below chance. However, a more potentially interesting outcome would be that during spontaneous imagery, both hyperphantasics and aphantasics have a decoding accuracy that is above chance in V1, while only in voluntary imagery, aphantasics have a decoding accuracy that is below chance in V1. That might suggest that the problem that aphantasics have is specific for voluntary imagery first, but also could be related to metacognition or second-order problem. Then another thing that I want to do is cross-decoding between spontaneous and voluntary imagery. Specifically, I want to train the classifier on voluntary runs and test in spontaneous runs to see whether it's still possible to distinguish the specific sounds in early visual areas. If that is possible, that might suggest that the two conditions involve similar representations. Then I want to test whether it is possible that whether there are significant clusters in our regions of interest that are modulated by the experienced imagery vividness during the voluntary imagery condition. And finally, I want to compare the decoding accuracy between my groups of participants, so highs and lows in imagery. So regarding the specific participants that I want to recruit, so the number, I know this number seems crazy, but my study wants to tackle individual differences in imagery, so the number has to be high. Of course, it has to be a trade-off between funding available and the best choice for power. My idea, so I was thinking about the best potential choices for my group. On one side, I could consider two extreme groups, aphantasics, so people that don't have any imagery, and hyperphantasics, those that say they have the strongest imagery as real life. The problem that I see here is the risk of ceiling floor effects during in behavioral ratings of vividness during the voluntary visual imagery condition, and also potentially biased participants. So my preferred choice for now would be to have aphantasics, so people that don't imagine at all versus people that are able to imagine normal images, considering a more heterogeneous sample. How do I define lows and highs in imagery? So nowadays we still use self-report subjective questionnaire to distinguish the different groups of images. The most used one is the vividness of visual imagery questionnaire, which assess the quality of the experienced imagery. But there is also another interesting question is the spontaneous use of imagery that is more about your daily use of imagery. Another important point of my experimental design is the selection of the stimuli, the sounds used. So veteran colleagues in the study, they didn't really specify why they choose specific stimuli, specific sounds, so they choose them arbitrarily. But in my case, I want to try to select the sounds that are the most appropriate to also induce and evocative to induce spontaneous imagery. So because of this reason, back in May, I ran this small behavioral pilot in which I asked around 67 participants to listen to 100 sounds. And I divided my stimuli in two major categories: animate, produced by living organism, and inanimate, so produced by non-living organism, each lasting 5-6 seconds, which will be the same time in my fMRI study. And I asked participants, I told participants that they didn't need to make any effort to generate imagery while listening, but just report what spontaneously popped in their mind. So the questions that I asked them that serves to categorize and select the sounds were, first, if they recognize correctly the sound as produced by an animate or inanimate organism, so if they recognize the sound. Second, whether they experienced any imagery at some point while listening to the sound. And finally, the vividness of the imagery experienced. Because the idea is to then select just the sounds that were recognized correctly at least 90% of times, and also those sounds that have the highest vividness and maximum duration of spontaneous imagery. And then I want to end up with half of the sounds produced by living animate organism and half of the sounds produced by inanimate, which will be the two main categories. Another thing I want to control for low-level features of the sounds. Regarding the number of sounds, that depends. And now it's another point to discuss, and I would love to discuss it with you afterwards. So basically what Vetter and colleagues did in the study was to have just 3 sounds that they repeated 30 times each, so a lot of time each. And that, however, can be a problem in my study. First, because that could be problematic for taking a trial-by-trial measure of vividness and pleasantness. And also because at some point participants might be disengaged. Remember that I will repeat the same sounds also in the voluntary imagery condition. So my preferred choice for now, which is option 2, I gladly did, is to have like for each of the big categories, living, no living, some subcategories that would be identified by a specific entity of sound. For example, duck, dog, traffic, and within these subcategories have different exemplars that represent the category. And in this way, to give also a better experience for participants. The third choice is the least preferred one, this option would be to have all different sounds. But in this way, that could be problematic, of course, for the decoding analysis, because I would only be able to contrast animate versus inanimate. So just a few more details about the experimental design. So below you can see like an example of a trial, of trial in both the 2 parts. So the idea is that each sound will be presented for 6 seconds, and there will always be a fixation cross both during the sound and during the intertrial interval. And the sounds will be presented in a pseudo-random order, so never repeated immediately. My ideas for now is to have at least 60 trials inanimate and 60 trial animate sounds in each of the 2 conditions part. And for each of these big categories, I have at least 2 or 3 sound subcategories, and each repeated 30 times in order to be able to decode the specific sound. And within these subcategories, I have different exemplars, at least 2 or 3 per subcategory. So in total, each part should last for about 22 minutes. So for a total of 44 minutes. With then the structural scanning and the tracking, I should stay within 1 hour, I hope. So yeah. Okay, so I explain you a bit about the study and the addition that I will make compared to veteran colleagues. But now I would like to illustrate you a bit, summarize the problems limitation, the things that I want to discuss with you. So first, about the choice of the stimuli, how many different sounds to have, how many repetition, at least, for each sound or exemplar should I have. Second, as I mentioned, I'm still deciding on the best participant group, the choices of my participant group to maximize power. And third, I'm still unsure whether pleasantness is a good dimension, is a good rating to ask participants during the first part, or whether it can be problematic for imagery. So if you have other ideas, suggestions, I'm happy to hear them. The last point is more a kind of conceptual problem. So during the spontaneous condition, we can be totally sure that people will actually imagine. I mean, I expect them to do so based on the pilot also, but we can be sure. And I'm thinking about potential way to control and improve this part. My idea is to ask at the very end of the experiment, when participants are outside the scanner, to listen to the sound one more time without repetition, and just from memory, report whether during the first part, the passive listening condition, they had any imagery. So yeah, sorry. So anyway, thank you. I want to thank you. I want to thank all my supervisors who are my collaborator, and also Chris was my collaborator. And also I want to thank you all for listening. Okay. Yeah.
Lovely talk. Thank you,
Yeah.
Julia. We've got quite a lot of questions in the comments. So
Okay. How do I open them?
If you click chat.
Chat. Okay. Oh wow.
But I will read them out. But people who've asked questions, if you prefer, you can ask them using your microphone. But first off, we've got Jules, who asks, have you considered varying valence in the sounds? So people with aphantasia, she believes, are more likely to have a flash of imagery when the object has a negative valence. Have you considered varying valence?
Okay. I mean, because the natural sounds represent some natural scenes. Yeah, I mean, I had some sounds that, for example, were like crashes or car accident or whatever, but most of the sounds are kind of neutral. I mean, a dog, I don't know. It's something that I didn't consider, but yeah, it could be potentially interesting. Yeah. Also for imagery, I think that valence can be important in general for normal images. Like intrusive negative imagery is usually more vivid because of its negative valence and arousal. So yeah.
I think as long as it can be well controlled, so that if you can vary on that dimension, then it's something without introducing confounds to other things that you care about, then it's something that you could look at as a secondary analysis. Yeah. Okay. Charlotte is interested in repetition suppression effects on the build signal. So having repeated repeated stimuli multiple times. Will a classifier work better with multiple instances of the same stimuli or categories?
Yeah, so I mean, Markley and Vetter and colleagues in the study remember that they have really no results, no increased activation in both signal, maybe because they repeated the same sound many, many times. That's why I think why it's better to vary a bit, to have different exemplar. But of course, as you said, like for decoding, you need to have at least a certain number of stimuli, the repetition, in order to be able to decode. And I think for my design, I'm more prone to favor the decode, like the multivariate pattern analysis. So yeah, I need some repetition.
It's true. You'll definitely get a boost in signal to noise with multiple repetitions, and that is always going to be, critical. And Alexa has made a similar comment to that. So, what would Ben Franks asks, what would the visual environment be for participants? Would you remove external visual stimulation?
My idea is that they have their eyes open. So if that was the question, so not blindfold them, also because I want control for eye movements with eye tracking. So I don't know if I'm answering the question.
What would be on the screen, I guess?
The screen is just like, I was thinking about potentially just noise, like, yeah, but I didn't really think about that. But yeah, fixation cross, they just have to remain focused on the fixation cross and try to be, and try not to move the eyes too much, I guess.
And do you plan to do eye tracking?
Yes. It's a crucial aspect. So.
Okay, Jules, perhaps the name of the sound, e.g. duck or traffic, should be matched for lexical frequency, length, and of course, imageability.
Yeah. So I won't use the names of the sound anyway. So yeah, I mean, I won't cue participants with sound names, but rather just ask them to imagine while listening. So I won't say.
It was really, it was a worry. Hi, thank you for a great talk and some really interesting hypotheses. It was just in case language is mediating in there somehow, perhaps, especially for aphantasics. But Alexa had some interesting comments on that too in the comments below.
Oh. Shall I come in sort of verbally, or is that useful?
That might be useful, yes. I'm not sure if I
think that, yeah, sorry, I've replied to a couple of different things. I was just thinking, thanks, by the way, sorry, thanks for a great talk. It's an interesting study. I wonder if you use RSA instead of a classifier, that might be better for a couple of different reasons. So one thing you can do if you use RSA is you can have comparison models. So if you're worried about the concept imageability as a potential confound, you could fit a comparison representational model that would address that. So I don't know how much you know about RSA, but that's one way you could do that, and you could also use that to test different granularities if you wanted to look at the kind of aspects that were represented in the two conditions.
Yeah, thank you for the suggestion. I actually read a couple of papers about RSA, but I'm definitely not an expert. As I said, it's my first fMRI study because I'm more experienced with.
Right, I missed that bit. I came in late. I mean, I can help. I mean, I've got my PhD student in Edinburgh's got an RSA study that we're just writing up, and I've got another one in the pipeline. So I've done a bit, not tons, but I can tell you a bit about how it would work. It's not any harder than MVPA. It's just a slightly different way of doing the same thing, basically. But it involves. But you know, either way, it's just the thing that struck me that would make it potentially useful would be you could potentially try and decode at the category level, such as its traffic, and then you could also say there are item-specific representations. In theory, you can use RSA at different levels, whereas if you use a classifier, you could do a multi-class classifier for all the different categories, but you wouldn't be able to do it at the level of items. So it has that strength if you were interested in that. If your hypothesis is not that detailed and you just want to look at the different categories such as traffic, then probably using classifier would be simpler.
Yeah, maybe it's something that I should take into account. Yeah, I wanted to repeat at least veteran colleagues' analysis, since the study design is quite similar and it's made exactly to do the same analysis. So I should read more about whether my design is appropriate also for potentially running an RSA, because I remember there were some specific aspects that you have to tackle in your design to be able to do so. So I don't know if it can fit.
It's probably pretty similar, but if you want to ask me about it at any point, feel free. I mean, I came in late and I didn't catch what your SOA is, but it's normally similar. You probably want to present your stimuli in a random order, because that's a good thing for a bunch of reasons.
I think it will work if you want to do that kind of analysis. I can't see any reason why you wouldn't be able to.
Yeah, exactly. I think it will work too, but yeah.
Okay, let's have one more question and then we'll move on to Jamie. So there's Ed. I'm sorry for the other people who I can't get to, but lots and lots of questions, and the chat will be saved so you can look at them and maybe have some offline.
Thank you for all the questions, though. I was worried that no one would have asked anything.
So from Ed, as a way to make sure you are measuring spontaneous imagery, you could contrast sounds that are easy versus difficult to evoke imagery from online pilot data. Also, I have experience of using CV Manover toolbox. Happy to share my experiences. So that might be an offline discussion, but yeah.
Yeah, thank you very much for your suggestion. The problem is that I guess if you mean including in the fMRI study stimuli that differ in the imageability, that would force me also to increase the number of stimuli, I guess. So that's one thing that I thought about, but I'm not sure, because I just wanted to have stimuli that I was sure that, or at least a bit more sure that would evoke the imagery. That's why I selected only the highest in vividness, that I guess also the easiest to imagine. I also think that the stimuli, it's important that people are able to recognize the stimuli, so that helps imageability of the stimulus. So that's also why I consider the correct recognition. But yeah, thank you for the suggestion.
Cool. Well, great stuff. Great job, Giulia. Let's switch over to Jamie. So if you can unshare your screen, and then Jamie can share his.
Shall I just go?
Yes.
Hang on, let's get it up.
So,
Okay, so this is a proposal that was based on an unsuccessful grant where I have a small amount of money to resurrect certain parts of it. And let me go through it. So most people will know what synesthesia is. They're these anomalous perceptual experiences that are induced by something. So maybe looking at black and white text will induce experiences of color, or listening to words evokes a taste of sausage meat, or you experience numbers as this sequence. So synesthesia is of interest in its own right as being this unusual way of experiencing the world, but this project is doing something slightly different. What we're doing is that we're taking synesthesia as kind of a marker of, I suppose, a neurodiverse group. And we're saying that synesthetes aren't just different in terms of these unusual experiences, they differ in terms of an underlying cognitive profile and an underlying clinical profile. And this cognitive and clinical differences are of interest in their own right, aside from any interest that we might have in these interesting experiences. And this is just an example of the kind of approach that shows that synesthetes have a distinctive cognitive profile. It kind of relates, I suppose, a basic example of what we would do with neuroimaging data, where we take, in this case, a relatively large group of synesthetes and controls, and we just throw a bunch of relatively standard questionnaires and cognitive tests to them. So we have tests of memory, imagery, and so on. These generate 33 different measures. So our measure of personality, for instance, has 5 different subscales. Our measure of memory has, again, different components to that. But what we find is that synesthetes kind of occupy a particular cognitive niche. And what we look at is, can we tell who's a synesthete and who's not by having a look at the way that they respond to these measures. So what we do is that we, from this set of 201, we effectively take one person out at a time, and then we compare them against the rest of the set, and we say who else in this set of 200 looks like this person in terms of their profile of scores. And then we ask the question, in terms of who looks like them, are they a synesthete or are they a control? So what we're asking is, for each person, are they surrounded by other people within their cognitive neighborhood who look like synesthetes or who look like controls? And that's effectively what we have here. So this is a measure of how many synesthetes you have in your neighborhood. So you can treat this as a binary classification, if you will, is that if you've got more synesthetes in your neighborhood, you think you're a synesthete, and less here. What we have here is that synesthetes, and the more types of synesthesia you have, the more your cognitive neighborhood is defined only by other synesthetes, in effect, that the people who look like you in this profile are all other synesthetes, not all, but mainly other synesthetes, and the controls have more of a spread. So what this means is synesthetes have a particular distinctive profile. You can drill down and show that synesthetes tend to be more hyperphantasic. So what Giulia was talking about, better memory, they're not different on every single measure. They go up on the autism spectrum. This also kind of guides us in terms of selecting people who we want. So we might want to focus again on the more extreme synesthetes, at least in the first instance, because this is where we imagine the strongest effect sizes would be, assuming that whatever's driving cognitive differences is also some brain level difference, and it must be there somewhere. We see a similar thing if we look at here. This is a full measure of autism. This is the autism spectrum quotient. And here, this is just taking a binary cutoff as to whether you're scoring very high on this measure or not. A score above 32 means that you are kind of up there with people who might be receiving a diagnosis of autism. And again, this is the number of types of synesthesia you have. If you have no types of synesthesia, you're like 90-odd% of the population who, are kind of a general sample. And the more types of synesthesia you have, the more up the spectrum you go, and in particular ways. Jules has done studies showing that they also are more likely to be anxious, but it doesn't apply for every mental health problem. PTSD is one that also comes up. So in grey, this is a meta-analysis of soldiers in American military. In black, these are 2 studies done on synesthetes who were also in the American military. And here you've just got the effect size. What is the probability of developing PTSD if you've been in a traumatic incident? And basically what it shows is that if you experience colors for letters and numbers, that's as big a risk factor as the actual severity of the trauma that you were exposed to in itself. And if you think that that doesn't make any sense, I would agree with you, because there's no logical reason why having colored letters and numbers would make you prone to trauma. What it must mean is that there is something about your brain makeup and the way that you think, your cognitive style, that is a vulnerability factor. And here the vulnerability factor is that if you can remember past events in vivid detail and relive them spontaneously, then that's rather like a PTSD flashback. But that is part of your cognitive makeup. That sometimes it's good to remember things and relive them as mental images. Sometimes all you want to do is forget them. So that's why we're interested in doing this, is the idea that synesthesia is indicative of a broad phenotype of important cognitive differences and clinical vulnerabilities. I kind of refer to this as something like a synesthetic disposition, that there is something like what it is to be a synesthete aside from these, the actual defining characteristics of what synesthesia is, and that there will be some biomarker. There's a whole idea that synesthesia is hyperconnectivity, but how that's actually instantiated is kind of up for grabs. So what I want to do is create an open science repository of synesthetic brains. This is not a magic number, I can say something about it, but also to have good cognitive and clinical data that is linked to it. So this is a good study, a good review paper in Nature Reviews Neuroscience about creating biomarkers here. In effect, what they advocate is creating kind of whole brain levels rather than just looking at regions of interest and so on to do that. And there are various ways in which you can do this. One of the key elements is that you develop your biomarker on one group and train it on another. So this is a standard kind of core kind of unbroken rule that you have to do in here, so that your training and your tests are separate. That's kind of what you've got here. And this is effectively the mountain that we're trying to climb here in terms of developing biomarkers. And the proposal is that I will get as far as exploration and to some extent demonstration of this. And the approach, if you look at how you kind of climb this mountain, is a kind of a whittling down of candidates. And that's effectively what you have here, is that you might start with I don't know, a dozen particular biomarkers, and then you look at the most promising, and then you take them into a second sample. So here it's one sample, and you maybe do leave one out, kind of cross-validation. Then you go to a completely new sample of synesthetes, and you see whether your best markers hold true and replicate. And this obviously gets around the multiple comparisons problem here, in the sense that you are then effectively whittling down. And then at these other stages is that you do replications perhaps on other sites, for instance, or maybe you take other kinds of synesthetes, so maybe less extreme synesthetes, for instance, would be this. And eventually maybe you get to population level. So there are things like the UK Biobank with 100,000 people in there. What you might be able to do is take a biomarker of this person has a synesthetic brain. You can effectively feed that into this 100,000 people, and you will then find the genetic markers for people who have that particular brain type and their life history and all the other things that goes with it. So that becomes the kind of the ultimate goal, if you will. But that's not where we're at. We're very much at this starting climbing the hill. So whoops, that's not what I meant. So basically here the actual experimental design is very much an off the shelf. So there are some interesting points where I would welcome your feedback, but the actual sequences that I'm adopting are kind of pretty much set in stone, because these are large scale projects of analyzing the human connectome that have already collected data, where we can effectively import that into the CISC scanner. The original study used young adults with this profile, and this later study has a different age profile here that kind of has ages missing. Here, these sequences were improved slightly, but the major difference is that they're shorter sequences. And this is because they were dealing with, for instance, children and older people who might fidget or have other problems about lying down for hours. So we can collect data which is basically structural T1, T2, and resting state within about 40 minutes using this particular off-the-shelf sequence here. What I would like to do is avoid spending money on controls, given that there are already going to be 3,000 controls available in the States, and spend my money on the synesthetes. But this will create a potential confound. All the synesthetes would be collected on this scanner, and all the controls would be collected on a different scanner. Supposedly, all these sequences have been harmonized to minimize this, but obviously I will need to do a certain amount of control, kind of quality control data here. And the question is how I would do that and what the best way is. So for instance, if I were to use this protocol, would I just assume that the missing age here is good enough to use those controls? So what is the kind of burden of proof? Here they've tried to test the same people on both sequences to show that actually they're broadly similar, but they're not 100% similar. Maybe I'll come back to this in a minute, but these are the no, I will do that in a bit. But in effect, this is what these sequences give you, is that for each person, you're effectively dividing the brain up into these different regions. These different regions are divided up in terms of their connection profile, which includes things like the amount of myelin, but also includes the functional connectivity patterns in resting state. And in effect, what it does is it groups brain regions. It defines the boundaries according to whether or not that region projects to, consistently projects to other regions in the brain and has a similar profile in terms of white matter, in terms of myelination and grey matter properties. But the idea is that everybody would have slightly different shapes and sizes here, and to some extent those can act like fingerprints that you can tell one person from another, but also you can have group differences. So other studies have taken this and they've scanned the same people twice. So what they effectively do is say, can I find this person from in a set of 300 brains just from the scan at time 1? And you can do that with near 100% accuracy just by test, retest, and trying to figure out which brain is which by looking at this particular pattern of things. So in effect, this is what you get out of your data pipeline. Is that you run it through this and it creates these parcellated surfaces. In effect, you would then get from this a whole set of different biomarkers, which you can then kind of extrapolate in various ways. So one thing that you would have is that for these 180 regions in each hemisphere, you can know, for instance, the surface area, the thickness, the myelin properties. So for each person, you would have something like a 1 × 360 matrix defined by this, defined by that. And each one of those would be like a biomarker in itself. You can then extend this by looking at what you call the interareal relationship. So here you're just correlating one region with another. So is the myelination in V1 correlated with the level of myelination in another region, and so on? You're effectively just looking at the inter-regional correlations, either in these kinds of domains or in terms of the functional biomarkers, or you can extract other metrics from this. So whether a certain region is like a hub in that it connects or lots to other regions, or whether it's more kind of on the suburbs, it feeds in or is an output but isn't really a central thing. And this will differ from person to person to an extent. And I won't go through this. This is just here to kind of give you an idea that there are a whole lot of studies that have looked at this in terms of creating biomarkers and fingerprints. And in effect, the approach would be like climbing this mountain of trying multiple approaches and seeing what works. But ultimately, what might work is obviously some combination of these particular features that in effect you take almost, not a meta-analysis, but something that is a conjunction of this. So maybe a synesthete has this particular profile and to some extent that particular profile, and you create in effect an aggregate marker that operates across multiple of these domains. So the constraints are that so far I've got £30,000 from a philanthropic donation. I think I can increase this a little bit, and I have various other pots of money, but that is kind of the ballpark. I'm looking at a 40-minute scan, and the costs are this, unless I get some pilot work or whatever. And these are the kinds of numbers that we would have as a kind of a starting ballpark. For the synesthetes, what I would do is that I would start at the most extreme, because these seem to have the most extreme cognitive and clinical profiles, and that's ultimately one of the reasons why we're doing this. And we would divide them initially into two groups, one which is in effect a discovery group that we try all these markers, and then a confirmation group in which the best markers are then in effect replicated. So we might do that in terms of when people arrive, that they just get assigned an odd or an even group at random, for instance, or that we literally toss a coin and they just get partitioned. You probably wouldn't want to do it that you test the first half of participants, the others, because you might get all the keen people coming first or something odd like that. The controls is one of the things that I would like feedback on, because basically I want to invest as much money on the synesthetes and as least money on the controls, but obviously there has to be an element of quality control against the data sets that are collected elsewhere for this. So the way that I imagine it is the synesthetes are being divided into two samples at the first one the discovery set, one the confirmation set, and the controls, in effect, we would have kind of two samples. We would have a CISC sample, and then we would have a downloaded sample from elsewhere. And this could be, it probably wouldn't be good to just take 20 or 30. What we could do is take multiple batches of 20 and 30. So in effect, you're creating an almost distribution of what you would expect the data to be. And obviously what we're trying to do is we're trying to show that find biomarkers of synesthetes. We're trying to show that this group here are different from both of these groups. But at the same time, there's an element that we need to do of showing that the CISC group are equivalent to the downloadable data that we can get online. And that is one of the things which is a bit of an unknown. What we'd also do, and this will be done online, is create a kind of a battery of tests that we know seem to work. Some are a little bit more exploratory than others. So we've got mental imagery, where this is fairly tried and tested. Intelligence and creativity, there's very little evidence about synesthetes in intelligence, but I think it would be important to look at. Personality and memory, there are known differences here. And on the clinical side, we know of differences within autism, sensory sensitivity and anxiety. This is a different anxiety measure that has three different subscales, one looking at somatic symptoms and one worry, and I've forgotten what the third one is, but it's about depression. We don't have any evidence of linking synesthesia with depression. So this is the final slide. So effectively, one of the things we're wanting to do is transform synesthesia from being this niche topic to one that kind of connects it with these more big science and big data approaches that are out there that are looking at individual differences. And that ultimately, this kind of connectomic biomarker of synesthesia could be useful for instance, subtyping or explaining variation in autism. There are already databases out there of 2,000 autistic brains, and we can see which autistic brains have a synesthesia profile, for instance, and see whether that predicts clinical or cognitive measures. And it can also help us understand how the brain generates unusual experiences per se. So there we go.
Thank you, Jamie. Very, very interesting talk and exciting project. There's a lot of comments about the control side of things, and I think I have one thing I could say to that. A lot of people are saying that it is important that you get at least some control data from this scanner, because you won't be able to separate the site of scanning acquisition. And I wonder, given the protocol you're using is the HCP protocol and is reasonably standard. I wonder if perhaps you could look at some other data that's being acquired here. For example, Jess Eccles, Neil Harrison, and Marisa, they have essentially done this exactly the same kind of acquisition as you with the myelin maps and the resting state, and they have control data and patient data, and so you could perhaps maybe use some of their control data. It was acquired at CISC, and you could try and match all of the parameters of the acquisition to what they did. And I don't know what the feasibility is in terms of ethics and stuff, but that might be something to consider, even if it's a collaboration with another study, because I agree that you need to get some control data at least from this center.
Yes, yeah, I emailed Marissa today and she couldn't make the talk, and I've seen that Mara's put something up there as well, so I will have a chat with her unless she wants to say something now. Yeah, I mean, in terms of Jules' comments, that's also interesting. So here, the point is that, synesthetes might differ on multiple ways. By comparing them with weaker synesthetes and stronger synesthetes, this means that they are kind of relatively matched in terms of, that they've all volunteered for research and this sort of thing. So that is something that I intended to do, but I intended to put that at the back end of the project rather than the front end of the project. But it is something that potentially could be done now or could be brought earlier. It's just a question of getting the numbers to work.
Okay, Jenny asks, could you have a control analysis which match the experimental analysis in other respects, but where the groups are not expected to differ? However, I think having at least some controls at the same time in the scan will be more persuasive.
Yes, yeah, that's right. I mean, the kinds of things I'd thought about here was also just partly just looking at their data set. So in particular, they used two sequences on people, I think, let's get this right. So 36 and above and 35 to 21. So you could almost take a group of people who took different sequences at age 35 years and 6 months, and those who are age 36 who were taken on the different scanners, and show that these people are not differing in those particular ways. And that way you can show that actually it's not to do with differences in the sequences, it's to do with others. But yeah, I'll have to have a think about that.
Ben Franks asks, will you be including those with ASD in all the groups?
Right, okay, this came up in the ethics, is that are we excluding on the basis of clinical conditions? And the answer was no, partly because we're interested in comorbidities. But what I did put in the ethics is that obviously we would exclude on the, if they can't tolerate the MRI session for whatever reason, that would be the grounds. We haven't asked about formal diagnoses, and we'd probably have to go back to the ethics. Obviously, we're looking at this more informally in terms of, I suppose, continuous measures rather than binary diagnostic cutoffs. But we're not excluding on the ground of that. That's right. So I don't think it's a confound, because otherwise you're not looking at typical synesthetes. But it's an interesting point.
Amelia asks, when looking at the cognitive profiles of synesthesia, did you compare synesthetes at the same time, synesthetes of the same type, or did you compare based on the number of types of synesthesia experienced? Yeah,
so that is interesting. I did delve into that with both of them, and it seems to me that it's primarily driven by the number of types. And you will get this also in the brain imaging data, that in my view there is something about their brains, a kind of a bigger picture story that will track synesthesia. But nevertheless, there will be differences within the synesthete's brain that's to do with the types of synesthesia that they have as well. So in effect, their brains are going to differ both in terms of having that particular type of synesthesia, but also in terms of whatever the bigger profile, that whatever it is that makes these people neurodiverse in the first place. So it is quite hard to pick apart, but if you've got a large enough data set, you should be able to do it, both in terms of neuroimaging, but also in terms of a cognitive profile.
Hao Ting has a comment. With some of the fMRI-based features proposed here, I've calculated them on non-HCP protocol, and there's not a difference that I can find. Also, some reference studies didn't use the HCP protocol in either pre-processing or data collection. Okay,
that's fine. I mean, I might just get in touch with you, Hao Ting, but thank you.
Paul Kinghorn asks, if you're trying to eliminate the site differences between your collection and the online database, but surely those in the database come from a range of sites. How do the owners of the database prevent site differences?
Yeah, I was rereading the horrible technical paper this morning about this. They're actually not coming from that many sites. So when I looked at the authors, they're coming from all over the place. But actually, the data acquisition isn't coming from all over the place for these 1,000 brains. So the original young adults was all done at the University of Washington, and it kind of fooled me a little bit, because when you look at the authorship, it looks like they're everywhere, and they're not. But they are looking at this, and they call it harmonization, is the way that they describe it. With that, yeah.
Mara says the main point is making sure that the difference in site doesn't fully overlap with the difference in effects of interest. In the effect of interest.
Exactly. So to some extent, I mean, it would be a bit risky. You could almost develop the biomarkers and then afterwards show that it doesn't predict site differences, but that would be rather than, yeah, you could almost leave the problem until the end. So in effect, you scan the synesthetes here, you test the controls there, develop the biomarker, then afterwards you do the quality control when you know what it is that you've found.
I think we've covered most of the questions in the group chat. If anyone has any more questions, I think there's a couple of minutes, but otherwise I think we should perhaps draw to a close. Next week we have 2 project proposals from Chris Bird's group, Flavia De Luca and Jess Daly. So 2 memory-related project proposals, which we're going to hear about next week. And other than that, thank you very much, Jamie and Giulia, for wonderful, exciting talks. Bye, everybody.